In this presentation, we will show how to use Mathematica / Wolfram Cloud to plot and fit data. We will be using data from Hubble's law. The data consists of a set of sets. So each data point is a set of an x value and a y value. So the curly bracket 0.032, 170, close curly bracket, that is one xy data point. Then we have a set of data points. So we have a set of sets. And we are calling our set of data Hubble. The method ListPlot, capital L and capital P, makes a plot, and we are plotting the data Hubble. So ListPlot square bracket Hubble, close square bracket, Shift Enter. We can add additional arguments to the ListPlot method in order to get labels for our plot. So we've added a second argument called PlotLabel, capital P, capital L. And then you see in what was entered, it looks like an arrow, but we didn't type that arrow. We typed a minus sign and then a greater than sign, and that was turned into the arrow. Don't try to type the arrow or go find an arrow and paste it in. Just type a minus sign and then a greater than sign. It will be turned into that arrow. So plot label arrow, quote, Hubble's data, end quote. Similarly, as the third argument, we can add the axis label. An axis label is an XY pair. We're going to label the x-axis and the y-axis in one argument, and so they are in the curly brackets. We can do fancier things and have some formatting to these, but we're going to keep it simple for now. So here's the result of our label. The plot label was the sort of main title of the graph, and axis label were the x and y axis labels. So we can get a fit to this data by using the method LinearModelFit, which takes as its first argument the data, which we called Hubble. And then as a second argument, it has this x in curly brackets, and as a third argument, x again. Now this notation seems a bit cumbersome at first, but you have to anticipate things that might be coming later. So we might be fitting data to more than one variable. We might have 3 or 4 variables that we want to fit our data to. And then the variable might occur to sort of different powers, say in a polynomial. So this, and then you say, well, that's not linear, but linear in this case means linear in the parameter. So if you go to a polynomial, the parameter is out front just a simple number by itself, so it is linear in the power, and that's what the linear here means. Okay, so I have two versions of HubbleFit and HubbleFit 2. In the second one, we've added a fourth argument that said included constant basis and used one of those arrows and said false. So this is a simple linear fit is a mx plus b, sort of a slope and an intercept. And this is telling us the constant, the intercept, should be 0. I don't want to include an intercept. I want the intercept set to 0. And so you can see in HubbleFit 2 that there is a slope but no intercept. What we will find is that a fit is much more complicated than just the slope and intercept, or just the slope as we had in the second version, but that there are a whole set of sort of statistical measures that come along with the fit that tell you how good of a fit it is and how much you might believe in the fit and so on. And so you can get a set of statistical measures on the fit by saying Hubble fit square bracket and then putting parameter table, capital P, capital T in quotes. And then we see things that statistical error and T statistics and P values. We recall that a P value is supposed to be small, say less than 0.05, less than 5%. And the P for this is HubbleFit, not HubbleFit 2. The the p for the constant is significantly larger than what we normally want to accept. And that is the reason why we also had HubbleFit 2, which eliminated the constant. Sort of the p-test sort of suggested perhaps it was not to be trusted. As we said, HubbleFit or HubbleFit 2, these fits are sort of complicated objects, and so if we want just simple, the basic equation out of them, there's a way to extract that, and that is using this method called normal. So if I say normal square bracket, HubbleFit 2, close square bracket, shift enter, I will get just simply the equation of best fit, in this case with the constant set to 0. And then we can plot that. So again, we're not doing ListPlot now, but plot, we have a mathematical function, so we go to plot, and so it's plot out 7 was just the simple equation gotten through normal, and then we have a range of x's that we want to plot over, and we choose roughly the same set of x's that were in the ListPlot, so in this case 0 to 2. The method show can be used to put things together, to put visual things together. So we are saying show square bracket out square bracket 3 comma out square bracket 8, and then close the square bracket of show. So we are showing two things combined into one plot, and out 3 was the list plot of the data with the axes labeled and the title, and out 8 was the plot of the normal version of the fit equation. And this then put them together, so we see the line going through the data. If we want the equation displayed, then we can add a third argument, this epilogue. So show out 3 comma out 8 comma epilogue arrow inset, and then the argument of inset was out 7. Okay, so out 3 was the list plot with the labels. Out 8 was the linear fit with no constant. And the epilogue is going to be something that we're adding to this, and we are insetting, we're putting somewhere in there. And out 7 was the equation that we extracted from the linear model. Note that that says inset and not insert. A lot of people want to turn it into insert, but it is not, it's inset. If we want to control where that equation is displayed, we can add an argument to inset, which is an XY pair. So now we see epilogue arrow inset square bracket out 7. That's what we want to display, and then comma, and then a curly, and then an X and a Y value. So I've chosen here an X of about 0.5. So if you go on the x-axis and see where 0.5 is, you'll see that the equation is above it. And then I chose a y of 800. So if you go to vertically to a value of 800, you'll see that's where that equation is displayed. So the middle of that displayed equation is at the point 0.5 comma 800. If we want to add some simple little y equals in front of our displayed equation, we have to do two things. Out 7, which was the normal version of our equation, is sort of a mathematical function. But if we want just the sort of letters and words of it, then we say toString. So toString open square bracket, then out square bracket, 7, close square bracket. That turns it into just the string of letters, and not something that can be plotted or anything like that, but just the letters, just the string. And then we want to add on more to that string. That's known as a string join. So now we use the method string join, and then we can say I want to sort of glue y equals in front of the string version of the equation.